We might decide that instead of running these processes in the order in which they were received, we instead would want to use shortest job first scheduling. In this version of a policy for CPU scheduling, we're going to associate each process with the length of its next CPU burst. And we're going to use those lengths in order to schedule the process with the shortest CPU burst first. As far as waiting time goes, shortest job first is optimal. It's going to give the minimum average waiting time for any given set of processes. But we can't predict the future with any degree of certainty. We cannot really know ahead of time what the length of the next CPU burst for any individual process is going to be. So first we're going to talk about the algorithm, and then we're going to give an example for how you can calculate the next CPU burst. In this example, we are assuming that all of these processes arrive at time 0, but their burst times vary. Process 1 has a burst time of 6, process 2 has a burst time of 8, process 3 has a burst time of 7, and process 4 has a burst time of 3. Now, because we are working with shortest job first, process 4 is going to execute first, waiting 0 time. Process 1 has the next shortest burst time, so it's going to run for an additional 6 milliseconds and have a wait time of 3 milliseconds. Process 3 has the next shortest burst time with 7, and it will run starting at time 9, going up until time 16 milliseconds. So its waiting time is going to be 9. And then process 2, which had the longest burst time of 8 milliseconds, is going to execute from time 16 to time 24. When we average the waiting times for these 4 processes, they are then going to be divided by 4 and result in an average wait time of 7. So now you try. We have 3 processes in our system. They each arrived at time 0, but they have burst times wherein process 1 will burst for 5, process 2 will burst for 7, and process 3 will burst for 2 milliseconds. Give it a try. Pause the video here. Because shortest job first is also non-preemptive, we are going to also have 3 boxes in our Gantt chart here, and it's going to start at time 0. You can check to see if your total Gantt chart worked, because the total time that is taken in the system should add up to the total of all of the burst times. So that would be 14. We are going to execute process 3 first, even though it probably entered the system third, because it had a burst time of 2. Process 1 has the next shortest burst time with a burst time of 5. We will add that to the 2 when process 1 started, and we'll see that process 1 is going to end at time 7. And then the last process, process 2, is going to execute for 7 milliseconds and end at time 14. The average wait time for this sequence of processes will be 0 plus 2 plus 7 divided by 3 for a total of 3 milliseconds. It is also, however, possible that not all of our processes arrived at the same time. That matters. It matters specifically in shortest job first because we can only consider for our process to run any process that happens to be in the system at the time that we are making that scheduling decision. So at time 0, process 1 is the only one that happens to be in the system. Even though it has a burst time of 6, which is clearly larger than time 3, process 1 gets to go first. By the time that process 1 is done executing, processes 2, 3, and 4 are all in the system. So the next scheduling decision is going to happen at time 6 when process 1 gives up the CPU voluntarily. At that point in time, process 4 will run, followed by process 3 and process 2 in ascending order of how large their burst times are. When we calculate their average waiting time, process 1 waited 0, process 2 waited a total of 14, not 16, because process 2 waited 16 minus 2. 2 was their arrival time. So in order to calculate our wait time for each process, we are going to need to make sure that we are subtracting the arrival time for that process from whatever time they started on the CPU. Similarly, process 3 started at time 9, but it came in at time 4. So that's going to result in a CPU burst of 5. And process 4 came in at time 5, was scheduled at time 6. So process 4 is going to have a wait time of just 1 millisecond. Now you try. We have not changed anything about the burst times for our processes 1, 2, and 3. Process 1 still has a burst time of 5. Process 2 has a burst time of 7. And process 3 has a burst time of 2. However, process 2 is now the only one that arrived at time 0. Process 1 and process 3 have just arrived at time 3. Go ahead and try your Gantt chart. Pause the video here. Just like in our first version of shortest job first scheduling and first come first serve, this is still non-preemptive scheduling, which means that each process will run to completion once it is on the CPU. We still start at time 0. Our total time should still be 14, and we are going to start with process 2 here because it is the only process in the system at time 0. But because it's the only process there, it's going to run for its full 7 milliseconds. It'll then be followed by process 3 for a total of 2 milliseconds, and then process 1 will go last with its time of 5 milliseconds. When we calculate our average wait time, process 2 waited 0. Process 3 entered the system at time 3, but was scheduled at time 7. So we can say 7 minus 3. But then process 1 was scheduled at time 9, but entered into the system at time 3. So because of that, we are going to find first the wait time for each process, and then divide by 3, which results in a total of 0 plus 4 plus 6, which results in 10 divided by 3.